Hi, my name is David.
Hi, I'm Alex.
Hi, I'm Ethan.
Hello, my name is Michael Younger.
Hello everyone, my name is Pohan Peter Ho, and today I will be presenting our project Conductance Stabilization on Analog Neural Floppy Chip. This project explores the exciting potential of rerun-based crossbar architecture in analog neural computing. Neural network technologies demands power-efficient, fast, and modular device, and resistive memory or ReRAM stands out as a promising solution. In this work, we design an image upscaling algorithm and compare it to machine learning based method to traditional approach like Lenzo's interpolation. A major challenge with ReRAM is conductance drifting, which introduce noise and inaccuracy in computation over time. To tackle this, we implementing the and elevate the two stabilization methods, incremental gate voltage and verify algorithm, and biphasic post stabilization. Our goal was to showcase how ReRAM can support efficient analog computing while addressing its inherent non-idealities. Let's dive into the detail of our project.
Let's get into the theory of the device. So, for the past year, our team has been working on an analog ReRAM array. And what ReRAM is it's a resistive memory. So, applying a voltage across these devices will generate a path of conductance, right? So, by controlling the amount of voltage that we put into the device, we can actually create conductance weights. And by putting these ReRAM devices in an array, we can create matrix multiplication. And with matrix multiplication, we can generate a purely analog neural network, which is a really interesting new technology. But right now, it's got a big limitation where the conductances drift over time. Like, they don't hold their values very well. So our team was focused on implementing algorithms to optimize and maintain those conductance levels as much as possible and reduce the amount of noise as much as possible.
For the stabilization theory, one of the key challenges in utilizing ReRAM device is conductance drifting, where the device conductance deviates from its set value over time due to its physical and material characteristic. This drift introduces noise and inaccuracy, which can significantly impact the performance of our analog neural network. To address this issue, we implemented two stabilization techniques: incremental gate voltage and verify algorithm, and biphasic post stabilization. The IGVVA method works by gradually increase the gate voltage of the device and verify the conductance until it reaches the desired level. This control adjustment helps minimize drift over time. Meanwhile, biphasic pulse stabilization applies alternative positive and negative pulse to the device. These pulses counteract the neural tendency of drift and reduce the overall noise in the system. By combining these two methods, we are able to see a significant improvement in our computational accuracy.
And I will be going over the convolutional background as well as the UNet architecture we used for this project. So 2D convolutions, general overview, we have an input image, we have a kernel, we have an output. The kernel gets run across the input, multiplying each one. It contains the weights, and we get some output. We can pad the input to dictate the size of the output. We can also stride, so that's going to dictate how many pixels we go by every single time when we multiply by our kernel. And we have some bias that we add to the end so that the numbers work out correctly. The UNet architecture background, we have an encoder and we have a decoder. So the encoder is going to have two different convolutional blocks as well as two different ReLUs, and that's going to go straight through. And then we are going to max pull that down into the next encoder and into the next one and the next one and the next one, each encoder block going down the line. And then we're going to go back up using a K and an upsample to each decoder up and up and up and up and up all the way through. And we're also going to channel stack the input to the output. And the idea is that we don't lose any information as we go through, but we change and we augment and we get more information from the kernels and the weights that we pass through it. The loss function we're going to be using for this was a Sobel loss and an L1 loss. So we sum those losses to go over the entire thing. The Sobel loss is dictated by these equations here and is essentially the gradient of the image. And the L1 loss is going to give us our color accuracy of the image, which is just a quick sum and division. The unit architecture can be seen implemented in Python here. As you can see, the encoder blocks go through and up. The res block is the final encoder block, essentially, and then we have the decoders that go back up. The upscale block, and then our final convolution block is actually slightly different. The in channels and out channels are flipped, and this was to make implementation on the chip much easier. Thank you.
Okay, now let's take a look at some of the results that we've seen. So we trained our image upscaling model, and it's working pretty well now. If you look at the images down below, there's a small butterfly, and then there's 3 larger ones. 2 of them were upscaled, and 1 of them is the original. So one's the original, one's from our model, and one's from a standard method, like SOS upsampling. So take a minute, pause the video, see if you can guess which one is which. Now, if you guess that the first one was from our model, you're correct. The middle one is the original, and the one on the right is Lanczos. You can see that the one on the right from Lanczos is much blurrier than the other results that we've seen. Meanwhile, the one from our model lacks a little bit in the fine details compared to the original, and you can especially see that the antenna are a bit blurry on the butterfly. But other than that, it's a pretty good result that we've seen. Now that we've looked at some of the digital results, let's look at how we actually implement this on the analog device. In the background, you can see an animation of how the red output kernel weights get mapped onto conductances for the chip. So first step is we take those weights, we split them differentially into the positive and negative. From there, we'll convert it into one long column that will convert into conductances. Those conductances can then be put onto the chip, and we're doing it in a differential manner. So there'll be 2 columns corresponding to 1 output. At the same time, we'll then have some input image that we're working with. We'll take a slice of that image, it's 3 by 3, and we'll take those colors, and correspond them to matrices that we'll also put into a column, convert the voltages, and then those voltages will be put on each of the rows of the array. And then we can read the current out at the end, take the difference of the positive and negative currents, and then map that back to the output that we want.
We took the standard deviation of the conductance values over time. These graphs was over a period of roughly 40 minutes. We did this for devices at various conductance levels, and this plot demonstrates the distribution of standard deviations depending on what conductance difference was set. These conductance differences are the differences of the positive and negative columns that we have used in our differential weights. The graphs demonstrate that IGVVA and biphasic methods seem to have improved conductance drift over time, but their combination, while being better than the normal method, did not improve the results further. The results here are these image upscaling results with different stabilization methods applied. In addition to the stabilization methods, an additional bias is added to adjust for consistent analog bias. What can be seen is that the certain stabilization methods seem to have better color accuracy when looking at the main color Pikachu. This can be seen easiest when comparing to both IGVVA and the normal method to the model. IGVVA is closer to the yellow of the model, whereas the normal result has a green hue to it. All of these results demonstrate that despite some improvement to the conductance shift, the primary issue that is seen in the convolution results is being caused by the random noise. Here, by increasing the number of dot products averaged, the output results can look better and better. However, the main drawback is that the time it takes to gather these results increases in parallel with the number of dot product average. Here are some animations showing convolution output from the chip as it generates each pixel for the output.
The methods that the team applied to try to reduce noise and conductance drift on the device, biphasic pulse stabilization and the incremental gate voltage verification algorithm, were actually effective. Over half an hour period, it seemed that biphasic stabilization worked better than incremental gate voltage verification at keeping the noise quelled and keeping the conductance drift from getting too out of hand on the device. However, a really interesting result that the team found was that actually mapping weights onto the chip using just IGVVA was much, much faster than mapping them onto the chip using biphasic pulse stabilization. So in the future, the team believes that there's really good optimization that can be done with the IGVVA algorithm, and it could work much better.